In this video, we will discuss mass and volume. We will begin by considering the importance of these for chemical engineers, and then we will discuss how mass and volume are related through the key physical property of density, or its inverse, specific volume. We will then make a final consideration of flow of fluid in terms of mass and volumetric flow rates, and finally, the velocity of fluid through a pipe.
So the reasons we are so concerned with mass and volume relates back to what chemical engineers do. So what exactly is that? Well, first of all, chemical engineers design and build various process units which involve some change of material, be that a reactor, heat exchanger, separator. All of these involve some change of material. Chemical engineers also make sure that everything is working well with said units, and also that irregularities are identified and controlled. Chemical engineers also make changes to processes to accommodate for changing qualities of feedstock, increased demand, etc., etc. So what do these all have in common? Well, chemical engineers must deal with stuff. And usually the big question is, what kind of stuff do we have, and how much stuff, or more formally, material, do we have? Whether it is mass or volume that we are concerned with, we will need to be able to convert between the two. And what connects these two material quantities is the physical property of density, given the Greek symbol rho. Now, the units of rho, or density, is mass per volume. So the equation is given as rho is equal to mass divided by volume. And the units that we can be given for density include kilogram per meter cubed, gram per centimeter cubed, etc., etc. The key thing here is that the units will always be of the form mass per unit volume. And generally, the density is independent for solids and liquids, meaning that it's a fixed quantity for both solids and liquids. But it is very temperature dependent for gases. That is, that the density will vary dependent on the temperature at which the gas is at. There is also another way to express the density, and that is of the form of specific volume, which is in fact the inverse of density, and therefore can be described as rho, the inverse of density here, or our volume per unit mass. And that can be given in the form of meters cubed per kilogram, centimeters cubed per gram. You'll notice that the units that can be presented for our specific volume are the inverse of the units given for our density. And to present our specific volume, we can also present it as the inverse of density, which is simply V over M. Now, another important material quantity is that of flow rates. So that is the rate at which material is transferred between process units. So this is quite important for continuous processes, but is still important for batch processes as well. Now, the flow rate that we can denote as simply the symbol with a dot above it. So for mass flow rate, we would denote this as M dot, so instead of M, and that is the units we could give, for example, for that is ton per hour. It could be kilograms per second, but the key thing to note here, it is mass divided by unit time. We could also present our material flow rate as volumetric flow rate, and that would be given, of course, with the symbol V dot. And the key thing to note here is that, again, the units could be any volume divided by any unit time. So for example, liters per minute, centimeters cubed per second, etc., etc. Also, it may be relevant, particularly for a reaction taking place in, say, for example, a reactor or a reactive stripping column, whatever it is, the molar flow rate may be important. And that is, of course, the molar quantity per unit time. So moles per second, pound moles per hour, etc., etc. And normally it is easier to measure volumetric flow rate. And the one thing that we note is just also that the symbol for molar flow rate is N dot. Now, as I said, it's normally easier to measure volumetric flow rate, and that's just based on measurement devices. We can quite readily measure volumetric flow rate, and then with our knowledge of our density, we can calculate our mass flow rate from our volumetric flow rate. The equation is simply the mass flow rate is equal to the volumetric flow rate multiplied by density, or m dot is equal to v dot multiplied by rho. Now here we have an example of a block flow diagram to represent our process unit. And you'll notice that we have volumetric flow rates, mass flow rates, and molar flow rates presented here. Now, looking specifically at our flow rate going in, we know that the volumetric flow rate and mass flow rate are related to density. So a challenge to you that you could choose to take up is try to determine the density of the inlet flow. Be careful here, you may need to convert some of your units to a common unit of measurement so that you're able to actually obtain a coherent density value. Another interesting idea related to the volumetric flow rate is that of the velocity flow rate in a pipe. That is, the velocity of a fluid through a pipe with constant cross-sectional area. If we know the cross-sectional area for such a pipe, i.e. a constant cross-sectional area is simply a pipe, not a cone, for example, but a pipe with constant cross-section. And the relationship for our fluid velocity is then given by the volumetric flow rate through our pipe divided by the cross-sectional area. And in such a case as the diagram shown, we could perhaps assume that our pipe will be cylindrical. If so, the area or the cross-sectional area is given by pi over 4 multiplied by our diameter squared. And the key thing to note here is that we must remember to use the same unit of length for volumetric flow rate and our area. So we must match these two if we are to determine the fluid velocity in our pipe.
In this video, we have considered the importance of mass and volume for chemical engineering design, supervision, and modification. We've also looked at how we can determine the volume associated with a component, and vice versa, by considering the density or its inverse, specific volume. Finally, we've talked about material flow rates in terms of mass and volumetric flow rates, as well as fluid velocity. These are particularly important for moving fluid around a chemical processing plant.